All right, let's talk about one of those things from math class that trips a lot of people up, permutations versus combinations. What is the difference, really? And why should you care? Well, let's get into it.
You know, the best place to start is with something we've all used, a combination lock. But think about it for a second. If your code is 10, 20, 30, you can't just dial in 30, 20, 10 and expect it to open, right? The order is absolutely crucial. So technically, it's a permutation lock. And that one little idea, that's the key to understanding everything else.
And here it is, the big idea in a nutshell. Permutations are all about lists. Think of a race. Getting gold, silver, or bronze are very different ordered outcomes. Combinations, on the other hand, are about groups. Imagine you're just picking a project team. It doesn't matter if you were picked first or last, you're on the team. If you only remember one thing, make it this.
Okay, so let's dig into permutations first. The one where, just like the name suggests, every little detail and every possible position matters.
So what's the deal with a permutation? Well, it really boils down to two simple rules. First, the order you arrange things in is super important. And second, you can't pick the same thing twice. It's all about lining stuff up in one specific sequence.
Let's make this real. Picture it. You're at the Olympics. There are 8 contestants. When you go to award the gold medal, you've got 8 people to choose from. Simple enough. But once that's done, you've only got 7 athletes left for the silver. And after that, just 6 people are left vying for the bronze. See how the pool of choices gets smaller each time?
So, how do we find out all the possible ways the medals could be handed out? Well, you just multiply those choices together. 8 times 7 times 6. That gives us 336 unique ways for those athletes to end up on the podium. That's a lot of different outcomes.
Now, of course, there's a fancy formula for this, and yeah, it might look a little scary with those exclamation points. That's a factorial, by the way. It just means multiply a number by all the whole numbers below it. But really, all this formula is doing is giving us a shortcut for what we just did manually. It's a really slick way of saying, start with n and multiply the next k numbers down the line.
All right, now let's switch gears and talk about combinations. And if permutations are the strict, detail-obsessed sibling, then combinations are definitely the more laid-back, easygoing cousin.
So what happens when the prizes aren't fancy medals, but just 3 identical, kind of disappointing tin cans? If I give a can to Alice, then Bob, then Charlie, is that any different than giving one to Charlie, then Alice, then Bob? Nope. The result is the same. They all have a tin can. The order is meaningless.
Think about it like this. If we're picking a team and we choose Alice, Bob, and Charlie, a permutation would count all 6 of these arrangements as totally separate outcomes. But in the real world, it's just one team. It's the same group of people. For a combination, all these different orders get squished down into one single group. And that right there is the big aha moment. All 6 of those different ordered lists, they're 6 different permutations, but they are all just one combination. A combination is just what you get when you take a permutation and get rid of all the redundant ways to reorder the same stuff.
And the formula for this? It makes perfect sense. You start by finding the number of permutations, just like we did before. Then, you just divide by all the different ways you could have rearranged the items you chose. In our team example, that was 6, or 3 factorial. You're just dividing out all the duplicates.
Let's look at a head-to-head comparison. Say you're picking a president, a VP, and a water boy from 10 people. The specific jobs mean order matters, right? That's a permutation, and there are 720 ways to do it. But if you're just picking a committee of 3 people, where everyone's on equal footing, that's a combination, and there are only 120 ways. Way fewer, all because the order doesn't matter.
Okay, now this is where things get really cool. These numbers that we get from combinations, they don't just live in a vacuum. They show up in some really surprising and beautiful places in mathematics.
The result you get from n choose k, as it's often called, is so important that it has its own special name, the binomial coefficient. And when you start arranging these values, you might notice they form a pattern that looks just a little familiar. And there it is. On the left, you've got the binomial coefficients. And on the right, you've got the famous Pascal's triangle. They are literally the exact same thing. This incredible pattern is generated simply by figuring out how many ways there are to choose a group of items. How cool is that?
So to wrap this up, let's pull the camera back a bit. These ideas of order mattering or not mattering aren't just one-off tricks. They're actually part of a much bigger, more beautiful system for how we count things.
Everything we've covered today, picking items without repeating them, are really just 2 squares on this huge, elegant grid that mathematicians call the 12-fold way. The permutations and combinations we just learned are right there. two key pieces in a much larger puzzle that basically gives us a roadmap for how to count almost anything you can imagine.
It really makes you wonder, doesn't it? What other basic ideas are just the tip of some deep, beautiful iceberg? So the next time you're trying to figure out a counting problem, just remember to ask yourself that one core question. Does the order matter? Because now you know, you're not just finding an answer, you're tapping into a truly elegant part of the mathematical world.